can we come up with another integral that we can approach in a similar way? Kind of like do something to the original integral, somehow produce the situation that I will have to use the polar coordinates and then solve it from there. I think I found an example. I came up with that myself. Let me demonstrate that for you guys. So I'm not sure about you, but to me, this is the greatest integral of all time. And that is the Gaussian integral, because the way that Gauss solved it was very, very nice by using polar coordinates. I'm just going to go over the idea real quick with you guys here first. Right here, we start with calling this to be I, which is the integral going from negative infinity to positive infinity, e to the negative x squared dx. But notice this is the same as the integral of negative infinity to infinity, e to the negative y squared dy. Because all we did was just change the dummy variable, so they are totally okay, right? Now, I squared, I'm just going to multiply this and that together, so we get the integral negative infinity to positive infinity, e to the negative x squared dx times the integral negative infinity to positive infinity, e to the negative y squared dy. And then we will put this into a double integral. So we have the integral going from negative infinity to positive infinity, integral going from negative infinity to positive infinity. We are multiplying this times that. The basis is equal, so we just need to add the exponents. So we just need to have the e. Both are negative, factor that out. So we have negative, and then we have x squared plus y squared, and then dx dy. And now we end up with a double integral. You see, this is worse than the original. It looks like it, but the truth is no, because we can use polar coordinates. Here's the deal. X squared plus y squared equals r squared. That's very nice. Secondly, dx dy is equal to dr d theta. Yeah? No. Don't forget the r. I did have videos on this already, and also the whole thing right here in detail. I will have the links in the description, so make sure you go check them out if you don't know how to continue. And I'll tell you though, the answer to this right here is square root of pi. Very nice, right? But to me, I've been wondering, it's like, can we come up with another integral that we can approach in a similar way? It's like I want to kind of like do something to the original integral and then somehow produce the situation that I will have to use the polar coordinates and then solve it from there. Well, I think I found an example. I came up with that myself. So let me demonstrate that for you guys. So here's my idea. I'm going to start off with an integral that's impossible to be integrated with regular methods or regular functions. Just that we couldn't integrate e to the negative x squared regularly, right? Of course, you can use the special function, but we're not going to go there. So let me look at the integral of sine of x squared. This is also just pretty bad too. However, the example I'm going to give you, it's a double integral to begin with, okay? I know. The Gaussian integral is the greatest of all time, okay? It's just like my construction, so I can use the Gaussian trick too, so yeah. Anyways, I will also need another part, cosine of y squared. Now, no matter which variable that you integrate first, you can integrate this, you can integrate that regularly and regular functions. So let me just put down dx, dy. Now, I need to pick a limit of integration for x. That is also a key for us to be able to use the trick nicely. What I want to do is, I want to have something that's very, very symmetrical. And what's the best thing for us to use besides the circle, right? Let's use the unit circle. So I'm in the x world, so this is y equals negative square root of 1 minus y squared up to x equals this, and x equals square root of 1 minus y squared. And then we'll be going to the y world, and because we are talking about a unit circle, we want negative 1 to 1. So this is the integral that I came up with that you can sort of use the Gaussian trick to do this as well, which is very, very nice. You want to pause the video and do it right now? Sure, go ahead and try it. Okay, here we go. First, I'm going to convince you guys the following. I am going to just swap x and y, and they will have to be equal. This is equal to the integral going from negative 1 to 1. The integral going from negative square root of 1 minus, I'm not going to put down y squared, I'm going to put down x squared, up to square root of 1 minus x squared. And then here, it's not sine of x squared, but sine of y squared. Here, cosine of x squared. dy dx. Are they equal? Yes, you can just use the same idea like earlier. It's just like you change the dummy variable. You could have put down sine of alpha squared times cosine of beta squared, d alpha, d beta, and then just change this to beta and all that stuff, right? Same thing. Imagine if I give you this as the original question, they will end up to be the same value. So I hope this right here is convincing enough. Now, the next thing that we are going to do is the tricky part. Here we go. I'm going to look at the red integral, and then I'm going to do the change of the order of the dx dy right here. How do we do it though? We'll look at the picture first, right here. Remember, this is just going to be unit circle, but I will still kind of draw the picture for you guys step by step. So we're going from y equals this to y equal to that. So we're talking about the bottom portion, like so, and then up to the top portion, like this. Step 1, step 2. And then we go from negative 1 to 1 in the x. So it's like this. This is the order that we are looking at. Now, what I'm going to do is, I'm going to switch dx dy. That's what we want. So in that case, what we are going to do is that I'm going to be looking at this circle. It's again the circle. But in the x world, I want to look at this portion here first. And what's the equation for this? That's precisely negative square root of 1 minus y squared. So we go from negative square root of 1 minus y squared and up to this portion, which is what? Positive square root of 1 minus y squared. And then what we're going to do is to cover it, right? And we want to go from like this. So in terms of the y, because we're in the y world, I need to go from negative 1 to positive 1. Does this limit look familiar? Yes, they are the same as the original. But guess what though? Just kind of forget about the original first. All I did was I changed the order of dy dx to dx dy. Alright? So that means the integral here stays the same. Sine of y squared times cosine of x squared. Yes! Just like that. Now, what I'm going to do is, this is my original integral, and I'm going to add up with this integral here. Check this out. So, this is our original integral, and this is the blue integral that I showed you. They are equal. I will call the first integral to be I. Well, in that case, so it's the second one. That will also be I. Now what though? Well, unlike the Gaussian integral, where we multiply the integrals together, here have a look. These right here are the same. This and that, what does that remind you of? Sine A cosine B, sine B cosine A. That should remind you the angle sum formula for sine. Yeah, so in this case, we will be adding the integrals together. On the left hand side, we will get 2i, and then on the right hand side, this right here will stay the same. Negative 1 to 1, and then negative square root of 1 minus y squared, up to square root of 1 minus y squared. This right here together is just going to be sine of x squared plus y squared. And the dx dy stay the same. Just like this. Very nice, huh? Now, have a look. We have the x squared plus y squared, and by the polar coordinates, that gives us the r squared. Likewise, just like what I told you guys earlier, dx dy is what? Is it dr d theta that easy? No, it's tricky. There's an extra factor r. Make sure to check out my other video for the explanation for this. Now, we will also need to fix this a little bit. Here, remember this is on the unit circle, so I'll put that down right here for you guys real quick. We have dr, so r goes first. So r is like the radius. You can think about it from 0 up to the radius, which is 1. So we have to go from 0 to 1 for r. And then for the angle, well, not just from 0, you do one loop, run revolution. That will be 2 pi. So theta goes from 0 to 2 pi. So nice. Now we just have to integrate. We have sine of r squared, and then all that is r dr d theta. And in fact, you can kind of break it apart because the inside here is just with r, and then just multiply the outside. So if you would like, you can also do like this. Then we can look at the integral going from 0 to 1, and let me write down the r first, and then sine of r squared dr, and then we multiply by the integral going from 0 to 2 pi of d theta. And this is technically like a 1, so just keep that in mind. Now, for this integral, we can just do a usual u substitution. So right here, u equal r squared, and then I'll let you guys finish. Like, remember, we have the 2, right? The derivative is 2r. So we have to have the 1/2 after the integration. So we get 1/2, and the integral of sine is negative cosine. So it's negative cosine r, and then it's a 1/2. And we go from 0 to 1. So this is the first term. Times this thing right here will just give you 2 pi. Now, if you plug in 1, you get negative 1/2 cosine of 1, and then minus plugging 0, cosine 0 is just 1, and that's a negative 1/2, minus negative 1/2, so it's plus 1/2. And then multiply by 2 pi. Reduce out the 2, so we get, let me put the pi first, and let me write down the 1 first, minus cosine of 1. Now, be careful. This is not the answer because the original integral is just I. What we did was 2i. So, divide 2 on both sides, and ladies and gentlemen, this integral is pi over 2 times cosine of 1 minus cosine of 1. That's it. And I do have to admit that this answer is not as nice as the square root of pi for the Gaussian integral, but I like this very, very much.